Carbocation rearrangements are changes in structure of a carbocation or something that can become a carbocation that will make that carbocation more stable. So it's worth remembering that more stable carbocations are typically more substituted, and tertiary is better than secondary, which is better than primary, which is better than methyl, and that we typically don't form primary or methyl carbocations. Now, the methyl carbocation would have to be in a molecule that only had one carbon, and it can't rearrange to put the charge on a second carbon if there is no second carbon. So really, we're not worried in this case about those, but we're considering primary, secondary, and tertiaries. Also, worth remembering that resonance is even better, although that's something that we're not really going to focus on much in this unit. Carbocations rearrangements fall into essentially what for us is three important categories. There are hydride shifts, alkyl shifts, which is usually a methyl shift, and then a specialized kind of alkyl shift called a ring expansion. Now we're going to take a quick look at each one and then look at a few examples in more detail. First, a hydride shift is going to occur when moving a hydrogen atom from an adjacent carbon to a carbocation carbon will create a more substituted carbon. Now notice in this case that the carbocation that we're shown is secondary because it has two carbons directly attached, and right next door to it there is a tertiary carbon. So only if we could get this hydrogen to move over, and when it comes with a pair of electrons, we'll X that hydrogen carbon bond and simply draw an arrow from that bond to the carbocation carbon. That hydrogen moves over, then we have quenched the charge on the carbon that was originally positive because now it has four bonds, and that charge has moved indirectly, moved over to that more substituted carbon. So we've gone from a secondary carbocation to a tertiary carbocation. So again, driving force, more highly substituted carbocation carbon, and more highly substituted is more stable. And we call it a hydride shift because a hydride literally is a hydrogen with a pair of electrons, like the anion of hydrogen. And this is different from a hydronium or H+ shift. And so that because the hydrogen is taking its electrons with it. An alkyl shift, or which is usually a methyl shift but could be another group moving, is when we have a carbon adjacent to a carbocation carbon or a putative carbocation carbon that doesn't have any hydrogens to move. So we'd be looking at a quaternary carbon. For example, we have a case here where the carbocation would be primary if it formed. And that's because the carbon that bears the leaving group has only one other carbon attached. In this case would be the carbon from the ring. That carbon, however, is quaternary, has no hydrogen, so it's attached to four other carbons, or 4 degree, and so it can give up one of those bonds to the carbon that bears the leaving group. And this is an example of a rearrangement that also occurs with the leaving group leaving. And either a hydride shift or an alkyl shift can occur in this way. And what we'd show happening is just like the hydride shift, we take that carbon bond this time, and we're going to move it over to the carbon that bears the leaving group. But in this case, because the leaving group has yet to leave, we're going to kick it out in the same step. And so this is a substrate that would normally have reacted SN2, and we can have carbocation rearrangements even when we don't have a carbocation. So we're using this to illustrate that example. And that puts the charge on that now tertiary carbon. So we have a much more stable carbocation. The last type of rearrangement, or the ring expansion, is technically an alkyl shift, but it looks different enough that we're going to give it its own designation. And this is definitely the trickiest type of rearrangement to visualize. Now let's say that we have a situation like this, where we're starting with a relatively small ring, and we could even be starting with a tertiary carbocation, which would make us wonder, well, why would there be a rearrangement at all? And if we just look at the product of the rearrangement, how would that be more stable if it's still tertiary? Remember from our studies on cycloalkanes that cyclobutane, or the four-membered ring, is a relatively highly strained ring, and so in what we're doing in this case, we're not making our carbocation more stable because it's more substituted, but we're releasing or relieving ring strain. So we're making the structure overall more stable. And if you notice what's happened, if you look carefully to see what's happened, observe that we have a carbon here that has one methyl. We have a carbon here with two methyls, and that's the case afterwards as well. But what's happened is that this third carbon in the ring, that's a CH2, has changed its attachment. So the bond broke between the circle and the triangle carbon, and it reformed between the triangle carbon and the square carbon. And so we draw this by Xing that bond and pointing it to the square carbon to indicate that the bond moved over that direction. Now, a couple of notes here. This is not something that we need to predict unless we're asked to, or we're given some hint that it's happened, which could be a multiple choice question where one of the answers is the result of a viable carbocation rearrangement. It could also be more direct question stating that a rearrangement is happening or is possible, or it could be a word problem where we're expected to predict multiple products when we would expect only a single one. And so we're going to anticipate some kind of hint that something is happening. If we're just asked to predict a product, we don't need to worry about the rearrangement unless we either have options or we're told or hinted at thinking about the rearrangement.